Hello and welcome to Unit 11 on angular variables. I'm going to begin this unit a little bit differently because I want to show you what the goal of the next 3 units is. Here it is. We're going to take everything we've learned thus far and apply it to rotations. So this unit focuses on angular variables. So we're going to learn about position, velocity, and acceleration. Also, the angular equivalent of mass, moment of inertia. We'll look at constant angular acceleration equations, all sorts of fun stuff along those lines. In Unit 12, we'll focus on the next 3, force, kinetic energy, and work, which becomes torque, kinetic energy, and work. And we'll have the ability, finally, to really roll things down a ramp rather than just having them slide. And then in the last unit of the semester, Unit 13, we're going to look at angular momentum. Okay. To begin this process, however, we need to learn another bit of basics. And that bit of basics is the subject of Part 1. We're going to learn about the cross product, sometimes known as the vector product. So what is a cross product? Cross product is one of 2 ways for multiplying vectors. You've already learned the first one, that's the dot product. Okay, and that second line is wrong. The result of a cross product, not a dot product, is a vector. You may remember that the dot product was a scalar, cross product was a vector. Okay, and again, apparently I can't edit because this should also be cross. The cross product is indicative of the perpendicularness of 2 vectors. So again, with dot product, we saw when the 2 vectors were parallel, the dot product became as big as possible. Here, with cross product, we're going to find that when the 2 vectors are perpendicular, the cross product is as big as possible. In order to be able to do cross products, the first thing we have to learn is what happens with our unit vectors. Okay. So with unit vectors, there's this lovely schematic which I found in your book, that I cross J gives us K, and J cross K gives us I, and it's this cyclical picture. Okay. It also shows us that if you go backwards, so for example, if I do J cross I get negative K instead of K. That's shown down here. Okay. We will make use of this in just a minute. First, let's look at the perpendicularness aspect of the cross product. So if I have A cross B, and because it's a vector, I've got to look at the magnitude. So I'm going to put absolute value signs around it to show that it is a magnitude. That is going to give me the magnitude of A, the magnitude of B, multiplied by the sine of the angle between them. Now, remember, if I graph sine theta as a function of theta, at 0 it starts and goes up. It hits 1 at pi over 2, 0 again at pi, negative 1 at 3 pi over 2, and 0 again at 2 pi. Okay. So you can see here that when theta is pi over 2, sine theta becomes as big as possible, which means my cross product is going to be as big as possible. So how do I calculate this in its full vector form? Okay. Let's consider 2 vectors. A vector A, which is ax I hat plus ay j hat, and a vector B, which is bx I hat plus by j hat. To calculate A cross B, I need to cross my 2 vectors with each other using the rules for unit vectors that we learned 2 slides ago. So I can do this by foiling. So my first term is ax bx with an I hat cross I hat. The second term will be ax by that one has an I hat cross j hat associated with it. Next term will be ay bx, and that is j hat cross I hat. And lastly, I have ay by j hat cross j hat. Two of these terms we can see automatically are 0. I cross I and j cross j are 0, so these two terms go away. I cross j, as we saw on that schematic, if you remember, it did this. I have x, y, and c, and it went around counterclockwise, so x cross y gives us c. So ax by, and that lands in the k hat direction, plus ay bx, j cross I is going the other way, and because it's the other way, that would be the negative k hat. Ooh, my hat is not landing on top there. Negative k hat direction. And that is A cross B. Now you may be thinking, this is a little confusing, a little much, and I will agree with you, but I know a trick. Okay, this trick works for vectors with 2 components like we have here, or vectors with 3 components. It will not work with larger vectors. So I can't use it, for example, if I have a vector with 4 components, which does happen in physics. There are many components sometimes to vectors. For this class, you'll be okay though. We're not going to get above 2 or 3 component vectors. So here is the trick. You take your 2 vectors. So again, let's let A be what we had before, but let's add on the z component. And the same thing for B. And you're like, okay, this is making things more complicated, Dr. Murphy. I agree. Yes. Okay, so what we're going to do is we're going to define a matrix, and don't get scared on me. The top row of the matrix is going to be the unit vectors. The second row is going to be the first vector of your cross product. So if we're doing A cross B, this middle row will be the components of vector A, and the bottom row are the components of the last vector. And now what we're going to do is we are going to take and rewrite, I don't want orange, hold on, rewrite those first 2 rows, add them to the end. Okay. The next step is to multiply the diagonals, and we're going to go down and to the right first. So our first term in A cross B will be AY BZ I hat. The second one, go down the next line, is going to be AZ BX J hat. And the next one will be AX BY K hat. Okay. Now I'm going to switch colors just for illustration purposes. Let's go to green. We're now going to multiply the other diagonals and go up and to the right. So I'm going to go this way. But when you're doing this set of diagonals, you subtract. Okay, and I'm going to group these under their unit vector. So here I have AY BX K hat. So minus AY BX K hat. The next one is this one. So AZ BY I hat. And again, with this minus sign, AZ by I hat. And then the last one is ax bz j hat. Okay, and as I said, this works for 3 by 3 vectors as I've shown here, or it works for 2 by 2 vectors just as well. Repeat the process, just lop off the last row there. One thing to notice about the cross product, the result of the cross product. If you look at the terms, so for example, if I look at the I hat terms, notice I have AYBZ, AZBY, so it reverses, and in each term I have all three dimensions. Here I have AY, so I have the Y dimension, I have BZ, and it is in the I hat or the X direction. If I look at the J hat direction, I have AZ, BX, and then J because it's in the Y direction. And then lastly, I have AX, BY. It's pretty obvious K is in the Z hat direction. Okay. So that is my trick. I hope it helps you. Let's look at some properties of cross products. First off, it's anti-commutative. Anti-commutative? Not as scary as it sounds. That just says that A cross B is going to be the negative of B cross A. Okay. It's also distributive. So if I have A cross B plus C, that gives me A cross B plus A cross C. We actually already used that property when we did our first calculation of a cross product. I'm not going to do an example of calculating a cross product using vectors in 2 dimensions. And I think I may have misspoke a minute ago about how to use the trick, but let me demonstrate it here for these 2 vectors and show you how to do it when you have vectors in only 2 dimensions. So we're going to find A cross B. And the first thing we're going to do is make our matrix. So I hat, J hat, K hat, you do need to keep that, 4, -6, 0. And then for B, it's 2, 2, 0. Recopy those first 2 columns. And start multiplying the diagonals. So first off, we're going to multiply down. Oh, that did not change color. Gonna go with it. We have -6 times 0, I hat, that goes to 0. 2 times 0, j hat, also 0. K hat, 4 times 2, so that's 8 K hat. And then going up the other diagonal, we have 2 -6 K hat, that's -12. But remember, when we go up, we subtract. So -12 subtracted becomes a +12 K hat. 2, 0, I hat goes to 0. 0, 4, J hat goes to 0. So A cross B equals 20 K hat. And we're done. Next question is, what angle does it make with respect to, or what angle does A make with B? So for this, we need a little bit of information. We need the magnitude of A cross B. The magnitude of A cross B will just be 20. It's in 1 dimension. You can Pythagorean theorem up that if you like, but I really hope it's not necessary. We also need the magnitude of A. That will be the square root of 4 squared plus -6 squared, which works out to be 7.21. And we need the magnitude of B, which is the square root of 2 squared plus 2 squared, which is 2.83. Okay, now that we have all of these magnitudes, we can find A cross B. equals the magnitude of A, magnitude of B, times the sine of the angle between them. So 20 equals 7.21 times 2.83 times the sine of the angle. That gives us that sine theta equals 0.98 and theta equals 78.58 degrees. Now pause for a minute because we have to be a little bit careful and remembering how sine, we also encountered this with cosine back when we did dot product, works. Okay. If I think about the graph of sine theta as a function of theta, it does one of these. When I use the inverse sine to find an angle, it gives me an angle between negative pi over 2, or negative 90 degrees, and positive 90 degrees. Okay. So it gave me this one right here. My question is that the correct angle? If I think about these two vectors, B was 2, 2, so over 2, up 2, that's here at a 45-degree angle with the x-axis. A was at 4, negative 6. 1, 2, 3, 4, 5, 6. Let's pretend that I can draw things properly. This was B, this is A, and you can see that potentially this is at more than a 90-degree angle. And it is, in fact. If you find the angle that vector A makes with respect to the x-axis, you find that this is 56.31 degrees. You can do that with a tangent very easily. And if I take 45 plus 56.31, that gives me an angle of 101.81 degrees, which is right here. Right? Equal value of the sine function, but just symmetric about 90 degrees. So the correct angle is not 78.58, it is 101.81. And to get from 78.58 to this angle, you need to first subtract 78.58, which works out to be 11.42. And then you need to take 90 plus 11.42. And that works out to be 101.42, which isn't perfectly the same as the other angle we got. However, it is close enough, and we do have round off error going, so consider it the same is what I'm trying to say. Okay. Drawing a picture helps immensely to determine whether or not you have the correct angle. Lastly, we have cross products. We can find the cross product between these two vectors mathematically, but what if what we really want to know is just the direction? What if we want to know just the direction? The direction is found via the right-hand rule. Okay. I will later, not today, record a vector showing me a video showing me doing right-hand rule examples. For today, this is what you're going to get. So if I want to find A cross B, the first thing I do is I take my hand and I point it in the direction of my first vector. So if I look at the example I have on the far right, far left, I'm going to point my hand in the direction of A, which means it is pointing to the right. Okay. Now, you have many options. You could do palm up, you could do palm down, you could do palm pointing towards the screen. Lots of options for how you point your hand in direction of A. The second thing you want to do, which isn't here, is you want to curl into the direction of B. but that means that your palm must point in the direction of B. So I want palm up. Okay. Then I can point my fingers in the direction of B, and my thumb gives the direction of the third vector C. My thumb is pointing over my shoulder, or equivalently, it is pointing out of the page. Okay. You might see notation for out of the page that looks like a circle with a dot in it. This is the arrow notation. So if you see this, this means out. And if you see this, it means pointing in. Again, it's called the arrow notation. When it's pointing out, it looks like an arrow coming towards you. You're looking at the tip. When it's pointing in, you see the fletching, so it looks like a cross. Looking at the middle example for A cross B. Now, this is one normally where I would take and rotate the paper, because otherwise you have to make yourself feel like Gumby to do it. But since I can't rotate a coordinates or computer screen, we're going to manage. So I want to point my hand towards myself. I'm going to rotate it so that my thumb is pointing upward so I can turn my fingers into B. And that gives me that A cross B, or C in this case, points to the left. For the last example, they're no longer 90 degrees from each other, but we can still make this work. I'm going to point along A, which is up and to the left, and then rotate my hand so that I can point into B. I'm not moving the full 90 degrees this time, but the idea is the same. And I get my thumb points into the page, which is into page. Again, using the arrow notation, I would use a cross. Again, there is a video coming, maybe not today, showing you how to use your right hand to do these directions.